is it lowers the temperature of liquid formation. Lowers the temperature of liquid formation. So when we look here at A and B, we can see that the melting point of B is much lower than the melting point of A. But I reiterate, melting points are virtually irrelevant in this class. Please don't refer to them at all. What does matter is the invariant point, because that's when liquid formation is initiated. That's the onset of liquid formation. But the state of complete liquefaction is defined by the liquid surface. So in this system, the liquid is initiated at T1, but all along the liquidous surface, the complete liquefaction is indicated there. And you can see that the liquidous surface is dropping from A to B. When that happens, we say that B is a flux for A. B lowers the liquid formation or liquefaction extent of A. Okay, so B is a flux for A. In this case over here, we would say that A and B are mutual fluxes because they both drop into a eutectic. And we'd probably say that B is a stronger flux than A because there's a bigger drop from A to B than there is from B to A. And certainly in the eutectic, these are both mutually fluxing to around the same extent. That's what a flux is. And what kind of invariant point temperature is that? A what? A monotectic. Okay. And if I have that, what do we call that? Nodal decomposition. And those can both be subsolidus, metastable. And what was that? A syntectic. S-Y-N, syntectic. And that also can be subsolidus, although I've never seen one, and therefore we would call it what? Oid. Syntectoid, monotectoid, eutectoid, paratectoid. All solid analogs of invariant points with liquids. And what do we call that? Degenerate eutectic. Okay. They're cruising in. We're getting a better turnout here. Okay. Unpredictable buses, I guess. All right, so I'm hesitant to move off of this for all the latecomers. But the first one's a eutectic, the second is a paratectic, the third is a paratectic. The fourth is a monotectic, and then the fifth is a paratectic decomposition. This is a syntectic, this is a degenerate eutectic. And for those of you coming in late, these are all on Moodle already. You've been sent these already. Now, how do I get another page? There, is that? Okay, good. Hit the plus sign. What is that temperature? One solid going to two solids. What is it? Paratectoid. Okay. And what is that temperature? One solid going to two solids. A eutectoid. Okay. What kind of melting point is that? What kind of melting behavior is that? Congruent melting. And what kind of melting behavior is that? Incongruent melting. Okay. Have I left anything off? Well, yes, of course, I didn't do the solid solutions. What kind of solid solution is that? An ascending what? Complete solid solution. So that must be a descending solid solution. There's a maximal, and there's a minimal. So those are your four types of complete solid solutions. And of course, we can have partial solubility in that direction. We can have partial solubility in that direction. And we can have mutual partial solubility as well. So those are your three variants for partial solubility. What was that? Remember what that was? That's a second order phase transformation. There's no latent heat. It's just a reordering of the atoms. So there's no two-phase region. And this is an exception of the 1, 2, 1, 2 progression because it's 1 to 1. It's just a different kind of solid solution based on the first one it came from. So there's the parent solid solution, and this is the reordered one. What was that? Secondary solid solution. The others were all primary solid solutions because they came out of the sides. So here are the primaries, and the secondaries, the horizontal lines. And what was that? One solid going to solid plus liquid on cooling. Here's your liquid. Here's your solid. So there's solid 1, solid 2, liquid 3. What was that? Inverse paratectic. Okay. What was that? Somebody muttered it. What did you say? Superlattice. Okay, that's a superlattice. That's again, it's a reordering, but in the case of the second order phase transformation, the parent solid solution and the new one are just closely related, whereas in superlattice, the parent solid solution has quite a significant crystallographic change. So one's a reordering and one's a restructuring. Yeah.
Just practically, how do you recognize that being labeled, the difference between a solid spinodal decomposition and superlattice?
Okay, well that's a good question because they look alike, don't they? One's subsolidus, metastable spinodal decomposition, and the other's a superlattice. And the way you indicate that is by labeling it on the phase diagram. That's the only way you could do it. Yeah, because if it were a spinodal, that would be two solid solutions in there, and this is just gamma, and that's alpha, a different crystal structure. Okay, but that's a good question because they look the same. I think I've got all the invariant points covered. Okay, so. Mini review here, over 15 minutes, but I find that sometimes it's a good idea because not everybody looks at their notes and it sinks in, so this is kind of the equivalent of looking at your notes at home. And I did go through it pretty quickly yesterday, so for those of you who were frustrated and couldn't get the drawings done in time, this is 4. Now, one of the things by which we're assessed is, do we give progressive feedback? It's pretty hard to do when you're teaching for a mere 2 weeks, but I'm going to give you some feedback here. If you understand these invariant points and are more or less familiar with them, you're up to date. But if you're completely perplexed by these and don't have any idea what I'm talking about, then you're behind. And you need to talk to some of your classmates, or you can come and ask me for a quick review. And if there's a group of you who have this problem, get together so I don't have to do it 10 times. If you've absorbed this material and it seems logical and you kind of get the drift of it, that's fine. I don't expect you to understand how to use this yet. But if you are perplexed and just simply don't understand, then you are behind, because I'm going to forge ahead on the assumption that everybody's got this. Here's a composition. I have equilibrated it, and my question is, exam question, do a quantitative analysis of the phase assemblage of this composition. Quantitative phase analysis of this phase assemblage. So what phases do I have present at equilibrium? What are they? A and AB2. And how do you know? Verbalize loudly and clearly for those who might not know.
The 2 lines bounded by
Okay, it's in a box. It's in a phase field, and the 2 sides, 2 end members are A and AB2. Okay, but that's what I told you. Whatever's on the side defines the phases in that field. So this is really critical to understand. These are the phases present in equilibrium. But I said quantitative, and that answer is qualitative. So if my composition were here, what would it be? No, what would it be quantitatively? 100% AB2. And if my composition were right here, what would it be? 100% A. So it kind of stands to reason if you go back to, I don't know, third grade mathematics, we can figure out what the proportions are, can't we? All we have to do is draw a line, and we're going to label this X and this segment Y. And the percent A equals what? Percent A. Third grade, guys, come on. What is it? How do I calculate how much A I have? Y over X plus Y. So that must mean, if that's correct, then the percent AB2 is X over X plus Y. All right, now, some people will get this wrong. It happens every year. They're going to turn them around. What I just have written is called the inverse lever rule. And the inverse isn't usually said, we just call it the lever rule, but it's called the inverse lever rule to help you not make this mistake. And that is, you might think that A would be X because it's close to A. But that's not right. Because 100% A sits right here. So this is 50% A. This is 75% A because it's closer to A. This is 25% A. So the further away we get from A, the more obvious it becomes that we have to go to the other side of the lever to get its proportion, which is Y. And you didn't fall into that trap. So this is correct. This is called the inverse lever rule. This is very important because I will ask you to do quantitative phase analysis to show me you understand the lever rule. Okay, not a big deal. The next exam question is, give me the quantitative phase assemblage of that composition at T1. I didn't ask you to do it at room temperature. I specify the temperature. So what is it? I'll move it a little bit to make it easier. So what's the composition? Is A a component? What's the other component? What's L stand for? Okay, liquid. So this is going to be like a suspension, or powder sitting at the bottom and the liquid sitting on top, or the powder floating on top of the liquid underneath. How much do I have of each? What's my answer here? What's A equal? How much A? Okay, that's cool. Except I've got one serious problem here. What's my problem? What have I forgotten to do? Which you never do if you're my student. Never. Or I will give you a withering blast. What's missing from this? You got it? Sorry? No, Something's missing from the analysis. What I wrote here is wrong. It's not complete. Yep.
Well, you said that it's only for that portion of y, so you're not minusing the right-hand side?
No, it's got nothing to do with it because I'm not over there. My composition is in the two-phase field A plus L. End of story. Okay. Let's go to another page and I'll show you what's missing. What's the difference between these two diagrams? Yes, that's correct. Can we take the thought process a little further? What's the difference between these two? They got it? They're both correct. Different versions of the same phase diagram. Both correct. What's the difference between them? Nobody got it? Kinetics in phase equilibria? No. No kinetics in phase equilibria. Only if I say we're metastable or rapid cooling, something like that. They're both correct. But they're different phase diagrams. Nobody knows? Yeah?
Need different percentages to get AB.
What do you mean different percentages?
So like for the left one, you need more percent of A than the one on the right.
Which is? What percent is that?
For example, the one on the left looks like 50-50, whereas the one on the right kind of looks like 30-70.
Yeah. So if the one on the left is mole percent, what's the one on the right? What's the one on the right? You know? Anybody know? Thank you. You two had to combine your brains to get the right answer, but that's good. I've never told you whether these diagrams are in weight or mole percent. And we have phase diagrams in both. They're both done. Now, on the exams, I usually put in, are these diagrams in weight, mole, or volume percent? And there's always some dodo head in the class who says volume percent. There aren't any volume percent phase diagrams, except one that I did from quantitative microstructural analysis. So nobody does that. They don't exist. Don't be the dodo head who gives me the dumb answer. This is mole percent. This is weight percent. How do you know that the one on the left is mole percent and not weight percent? Come on, that's easy. What is it? Yeah, AB is stoichiometric, 1-to-1 ratio, 50-50. It sits right there in the middle of the diagram, so it's obviously mole percent. Now, every year I get some other dodo head who says, when I ask, is the diagram in weight, mole, or volume percent? And the guy goes, I give him a diagram like this. And he says, the diagram is in weight percent because there's no AB at 50-50. I just use AB as an example. They're all stoichiometric, for God's sake. But every year I get somebody who does this. Oh, where's your brain? Oh. Okay, don't be the guy who does that. That's really bad. It's demoralizing. Everything has to be stoichiometric unless it's a solid solution, and then who knows what it is. It's all over the place. So I'll always give you a diagram where it's clear you can figure it out. Except one time on an exam, you couldn't tell because there were no intermediate phases. So the answer was, we don't know. correct answer. All right, so now you got one other thing under your hat. Whoa, that's not what I wanted. How do I go back? Oh, good. All right, so in this diagram, I've got a congruently melting compound and incongruently melting compound. And the two end members, of course, are congruently melting. And I'm going to do something called an isoplethyl analysis. Okay. Now, do we know what an isotherm is? An isotherm is a line of constant temperature. So on this diagram, here's an isotherm right here. So any line's an isotherm on a phase diagram like this. Do you know what an isobar is? It's a curve or a line of constant pressure. An isoplet is a line of constant composition. So I'm going to do an isoplethyl analysis right there. I take that. And that's my exam question. For the composition 60% A, 40% B, or for the composition 50% A, 50% AB2, or for the composition 80 A2B, 20 AB2. They're all different ways of showing the same line. Do an isoplethyl analysis. So what I want to do is take this thing up to liquid state, cool it down, and tell what happens upon the cooling process. Okay, so let's do that. So I take it up into the liquid region, so I have a homogeneous liquid, and I start to cool. And when I cool it down to here, what happens? What happens? Oh, everybody should be able to answer this very, very quickly. If you cannot answer this question very quickly, very easily, you are behind. Okay? How do I answer this question? What's the best way to do it graphically? What do I need to do? Label the phase fields, that's right. So now I re-ask the question. When I cross that liquid surface, what happens? A precipitates. I'm in the two-phase region, A plus liquid. So A is a solid, and it's in a mixture with the liquid. So it's precipitated out of the liquid. We started with homogeneous liquid, A's come out. So either sinks to the bottom or floats to the top. So I'm precipitating A, right? Precipitating A. So what's happening to the composition of the liquid as I precipitate A out of it? Or it becomes deficient in A, which means the composition of the liquid is moving away from A toward B, isn't it? Right? And I know exactly how that's going because the phase diagram tells me it moves along the liquid surface. So that's the liquid composition. So, stage 1, homogeneous liquid. Stage 2, A precipitates. Next thing, the liquid moves away from A on the liquidous surface. Okay? So it goes down until it hits an inflection on the liquid surface. What happens there? Or it'll be easier not to follow the liquid Follow the solid. Or follow the isopleth. What happens here? What happens at that temperature? Sorry? What do we call that thing I just hit? That's a paratectic, isn't it? A2B goes to A plus liquid. The paratectic. So it's a paratectic reaction. So I'm going to write the paratectic reaction out. But I'm going down, right? So I'm going to get it in the right direction. So A plus liquid goes to, what does it go to? It goes to A2B. But I'm not on A2B, am I? So I'm just giving the reaction. So I'm right on the line, okay? Only on the line. As soon as I go below the line, what do I have? What's in that phase field right there? A2B and? So that must mean something else is precipitating. What is it? A2B? Did I precipitate A as the first precipitate? The primary phase? Did I precipitate A, the first thing to precipitate? The primary phase? Yes or no? Yes or no? Did I do that? Come on, guys. We just went through it. Raise your hand if the answer is yes. Raise your hand if the answer is no. Raise your hand if you don't know. Okay. All right. When I took you up into the liquid region, it was a homogeneous liquid, and we crossed over the liquidous surface, and what happened when we did that? We entered the A plus liquid region, which means A is precipitating out of the liquid. So, of course, A has precipitated from the liquid. That's the primary phase. Now I go down. My secondary phase is A2B. What happened to the A? Do I still have A there? I'm in this phase field right there that says A2B plus liquid. Do I have A written in there in that phase field? Yes or no? Do you see A written in that phase field? Yes or no? This phase field right here, do you see the letter A written in there? Not as part of AB2. You see it A as the phase precipitating, yes or no? No. So that means at equilibrium, I do not have A. So what happened to A? It precipitated. Where did it go? It was resorbed. We had a paratectic reaction. Look at the paratectic reaction, which I wrote in the right direction. A plus liquid goes to A2B. So in other words, A and the liquid underwent a paratectic reaction to form A2B. Now I use the word resorbed. The reason for that is, according to the phase diagram, it happens instantaneously. But that's not really what happens. It takes a while for it to dissolve. So we call that resorption. So here's where kinetics comes in. Not supposed to, but this is the real world. So A is being resorbed, and if you say that, that's fine, but if you also say that it disappeared through the paratectic reaction, that's also fine. Both answers will be correct. There's different ways of viewing it. So I'm precipitating A to B, and I'm doing that all the way down here until it hits another isotherm or another horizontal line at which there is an invariant point. What kind of invariant point is that? What kind of invariant point is that? That's a eutectic. Okay? So when I hit that eutectic, I have a reaction. And that is liquid goes to A2B plus AB2. But you might be sort of scratching your head saying, but I'm not at the eutectic. But when you're on that line, that's all we care about. Like I said, we're never really on the line. We're either above it or below it. But right now, we're going to say we're on it. And we're looking at it at a eutectic reaction. That's the eutectic reaction. Okay, and then when I go below it, what do I have? Yeah, which is the product of the eutectic reaction. Anyway, it's just not at the composition of the eutectic, it's at the composition of the isoplot. Okay. So at the end of the day, I have A2B plus AB2. Okay? And that's an isopletal analysis. So you just kind of follow what happens as you take the temperature down on one composition. Look what phase fields or phase assemblages you enter into. Give me the invariance points as you cross them, and you've got it right. So at equilibrium, the microstructure will consist of A2B and AB2, if it's at equilibrium. But if it's been cooled more quickly than equilibrium can handle, I'm going to have maybe some A, primary phase, still hanging around. Yeah?
When the eutectic reaction happens, when it goes down, does the AB2 come just from the liquid there, or would some of it come from the A2B?
Not sure I've got your question. Are you talking about the eutectic here?
It goes from A2B plus liquid to A2B plus.
Okay, that's a good question. Here is your liquid. That's actually your lever right there. I gave you the reaction, but the phase assemblage on that line is A2B plus liquid. Okay? So that's what I have at that point. So now think, it drops into a solid, and AB2 is precipitated, but it's not just AB2, it's actually a eutectic that's solidified, but we're not quite there yet. I have to tell you about microstructures. So your phase, your lever, is A2B plus liquid when you cross that line. But I want you to give me the invariant point reaction, because that's what happens. But physically, you have liquid in equilibrium with A2B. And so when it solidifies, I'll have to explain that. I'll do it shortly. It's not going to be entirely clear right now. So you'll notice that I stopped at the lowest temperature. I have three horizontal lines, don't I, in this diagram? Which one's the solidest temperature? I've got three possibilities. Which one is the solidest temperature? Raise your hand if you don't know the answer to that. Okay. I told you that the definition of solidus is the lowest temperature below which only solid exists. So it's always the lowest horizontal line, or the lowest invariant point. And the lowest invariant point is almost always eutectic. But those are both eutectics there. But one's lower than the other. So the solidus temperature is the one we just have been looking at. It's always the lowest. And you need to be aware of that because I asked this on an exam. And then something else that you'll need to know in the exam my observation from these exams in this class and in next year's class is that up to 60% of the class has forgotten how to convert between mole and weight percent. That is appalling, atrocious. That's high school chemistry. So I usually give an exam question that requires you to do it. And then if you fail, I have a mark on the exam. And I tabulate that and I report that at our exams meeting. This year, 42% of the class cannot convert between weight and mole percent. It's just unbelievable. So you need to review how to do that because it's hugely embarrassing that we would turn out graduates who can't do that simple calculation. Okay? That's really, really bad. I'm going to take a composition here, very simple system. I'm going to liquefy it completely, and notice I use the word liquefy. I don't use the word melt, because melt is very specific. It's an invariant point conversion from solid to liquid of the same composition. This is not melting, this is liquefaction. So I've got a homogeneous liquid. I'm going to cool it down. I'm going to cross over the liquid surface right there. And I'm going to enter into this region. And what is the label that I put on this phase field right here? A plus liquid. Okay, so A is precipitating out of the liquid. So up here, my microstructure is completely homogeneous. No features at all. But here, A has precipitated as the primary, or the first phase to precipitate. What's the crystal structure of A? According to this crappy drawing. What's the crystal structure of A? What is it? Those are squares. They're supposed to be squares. So what's the crystal structure of A? Probably cube. Now, I've got a liquid, and A is precipitating out. And as it does it, it has virtually no constraint imposed upon it physically, which means it's free to crystallize and not be compressed. So it's going to be very likely to form up into nicely shaped crystals. So very frequently you'll see nicely faceted crystals as your primary phase. Okay. And then I come here. And I told you that this lever right here is between A and liquid. Well, what have I got? A and liquid, right? Here's the liquid. Okay. A and liquid. And when I drop just below that, it's all going to be solid. That liquid, does that liquid have a specific composition? Does it have a name? The kind of liquid it might be? Any idea? Or is the question too vague? Who thinks the question's too vague? It's the eutectic liquid, isn't it? That's the eutectic liquid. Okay? That's a special liquid. Eutectic is very special. Because when that eutectic liquid solidifies, it doesn't just solidify some crappy old liquid, whatever it does. It doesn't work like that at all. It's very special how it recrystallizes. Okay, so it's really important to understand that there's a lever there between your primary phase, or secondary, whatever it is, and the eutectic, because it is the eutectic liquid that's precipitating, and that does something unique. Well, that's not unique. There's 3 variants of a solidified eutectic liquid. Okay. So here's your liquid, the eutectic. And when we go down here, we're going to have a microstructure that will consist of primary phase A plus solidified eutectic liquid. Okay. So here are my A's again. And I'm going to draw this particular eutectic as a rod-like eutectic. So it's going to form a grid of rods. And these rods might be aligned, but that's only in special special circumstances. They're supposed to be kind of aligned, but it moved. Okay, but I'll do you a better drawing in a minute. Okay? I spent my master's degree growing crystals like these. So a eutectic is a unique or an unusual looking thing. I'm going to show you the 3 main types of eutectics. The first is a rod, and we're not going to get these all aligned like this. These are going to be in different orientations. So you're going to see these domains. There's going to be one orientation that way, and like that, and that, and that, and that. But they'll all have the rod-like eutectic. Okay? So the rod is one phase, and the matrix is another. So I haven't drawn much of a matrix, so these actually should be bigger to correspond to the composition of the eutectic. Man. I don't know what's going on. Okay? So if the eutectic's at 50-50, then I should have a 50-50, depends on molar weight. And then, of course, that depends on the specific volume of the solid. These things I don't know. Or the density of the solid, if you want. And that will determine the volume percent. And that's what I mentioned. I can take a microstructure, and I can take the volume, and then I can assume a density, or get a reasonable estimate from the book, and then calculate the molar weight percent phase assemblage from that volume percent, but not many people would bother to do that. The second kind of eutectic is a plate-like eutectic. And usually you pick them apart when you etch them. One's dark and one's light. So you have plates. And these are domains here, grain boundaries. Okay? And the third is called Chinese script. It's really nice. I grew one of these in one of the systems I was investigating. So it looks a bit like that. So when the eutectic solidifies like that, at one temperature, not gradual, it forms one of those 3 kind of microstructures. All right, so that's what's special about these things. Now, think mechanically here. You think there might be an advantage to having a eutectic microstructure in, say, a tool, a mechanical tool that you're trying to make? Did you see an advantage or a disadvantage to that? Do you know anything at all about mechanical properties yet? Have you had anything in that? Yes or no? Come on, guys, it's a 50-50 question. Have you had mechanical properties or not? Yes? Is that a yes? Okay. So then you know about crack has to go around or it has to go through. And each one of those takes energy. So anything that you can steal energy from a crack is going to improve the toughness and probably the strength. And if you have a finely divided microstructure of platelets or rods, that's maximizing your number of interfaces. So that would tend to give you good properties, good mechanical properties. Furthermore, if your primary phase is a hard phase like a ceramic, then the crack really has a hard time because it goes along and says, oh, this is a squishy metal, I'm just going to shear it apart. Pretty easy getting those atoms to slide and so on. And oh, what's this? That ceramic is ionic covalent bond, not metallic. It's not squishy and slidable. It's all rigid and hard, and the crack can stop. What's the well-known material that is made using that principle? With a hard ceramic precipitate and a metallic matrix? What's the very famous that you all should know? Anybody know? No, it's called steel. Fe3C is the ceramic precipitate, a carbide, hard carbide. That's steel. Do you know how to make cast iron? Cast iron is made by throwing in some silicon. Now you can't understand this, but if you have ternary phase equilibria, you'll know that by putting silicon in, it completely changes the phase diagram. And instead of getting a carbide form, you actually get graphite. Graphite's plated and it peels apart really easily because it's van der Waals forces holding it in place together. And that's why cast iron is often machinable, because you're breaking open the graphite platelets. That's why cast iron is so much weaker than steel. It's a different microstructure. And you can interpret the microstructure from the phase diagram. I do this all the time. Look at a microstructure and then try to figure out what's going on from the phase diagram, or vice versa. Okay? So, we have that as a simple case. What if we have this? What kind of microstructure might we get if we go down through there? Well, I know it's going to precipitate. First, the primary phase is A. And when I hit that paratectic temperature, A gets resorbed, maybe. It's going to start to resorb anyway. And AB starts to precipitate. And then at the end of the day, I get a eutectic with AB as my secondary phase. But my problem is this A. So A is supposed to disappear right here. But it takes time for this to happen. And so usually what we do is we say that A is resorbed along this curve. And that's called a resorption curve. You'll get this in ternary phase equilibria as well. It's a resorption curve. And this is the time during which we expect and hope, maybe, A to resorb. But sometimes it does it and sometimes it doesn't. What would happen to the microstructure when I've got a non-equilibrium phase in there that's resorbing? What would the microstructure look like? At the end of the day, what happened is, maybe I shouldn't do it at the end of the day. I'll take you here. Here, I'm just going to draw one A grain, okay? And then I'm going to have some ABs here. I'm going to draw these as trigonal dudes. Okay? A doesn't want to be there. I got to get rid of it. If it's resorbing, it's going to redissolve in the liquid, won't it? It's in a liquid, and a liquid's a fast diffusion medium. So A is going to dissolve. And what's going to happen to A is the high surface area corners are going to dissolve off, and it's just going to slowly resorb, leaving you with a more rounded particle. Okay? And that's okay. That's okay. But I've still got some A left when I go into the final stage, down here. And this A particle here is in the solid state, and it's still coming down. And what happens is that it gets smaller, and there's a fuzzy region here. And that fuzzy region is a big fat pore, because if you dissolved it away, what got left? It's all solid, so it's not going to need to be liquid flowing into the pore. So as it dissolves, you end up with a gap. And of course, there has to be diffusion medium, so it's kind of a fuzzy thing, but it's mostly void. And so you end up with what's called coring. And so you have a discrete grain you can see in the middle, and then there's kind of a hard to visualize region around it where it was resorbing, and then the matrix outside of it, which is eutectic, and the secondary phase. Coring. Now, in your Moodle handout, I've given you a nice handout from a metallurgy book. The metallurgists usually do a very nice job of showing how the microstructures change as you cool down. There's quite a few examples in there for you to show that. So you can consult with that to get more information. And this is one of the key connections you make with the phase diagram, is how the microstructure might look. In gems, sometimes you see a faceted void. You go, how on earth did that happen? How did I get a hexagonal or a cubic void forming inside of a single crystal gemstone? How weird is that? Think about it, you know exactly how it happens. The gemstone precipitated as a single crystal, but it had a primary phase grain in it. But the primary phase was soluble in the crystal. And so the gemstone probably sat there for thousands of years near a volcano. All this heat allowed solid solubility to take place. So as you dissolve that primary phase away, what was left behind? A pore. I recently had a student come to me, and he had a really weird result. We were annealing some thin films, and the refractive index as a function of the annealing temperature was going down. This is really bad. It's supposed to go up, because as you increase the annealing temperature, you're putting more energy in, so the lattice becomes more regular and denser, so the optical density increases, which raises your refractive index. And ours was going down. Oh my God. Do it. And then we knew from other studies that the thing was heavily contaminated by boron. And B2O3 has a much lower refractive index than the matrix. And I said, well, that'll drop the refractive index, but that doesn't explain why it goes down, because when we heat it up more, this boron evaporates very readily. And I said, so if I reduce the boron, I've got a composite, and the refractive index of this composite will drop because of the mixture of the high and the low refractive indices. But if I'm removing the low, it should rise again. So the recrystallization and the exit of the boron both should raise the refractive index, and it dropped it. I was scratching my head, and then I said, well, wait a minute. When the boron exits, what's left behind? I said, it's a pore. And what's in the pore? Air. So what's the refractive index of air? 1, which is the lowest you can get. And I said, so I'm creating pores, so I got a 3-phase composite, and that's it. It's a bit shifty, but I can't think of anything else. your microstructure and you know your properties, then you can do these kind of interpretations. And sometimes you get really strange results, like a faceted pore. A faceted pore? How on earth would you get a faceted pore in a grain? Think about it. Understand it's a very simple process, and then you can figure it out. Ditto with a refractive index. That was a really weird result. So, these are the kind of things that we do when we're looking at our data. Sometimes we have to explain strange things. All right, I better give you a 5-minute break. Oh, God. Yeah.
Just going through the notes I from class with the notes posted online, and on a technique there, it says next to it it's similar to the constant volume point, but that doesn't.
Constitute points on top,
Yeah.
and the monotechnic temperatures underneath.
So is it when you just say monotechnic, does that include them both together? Is that why it's...
Yes, they're always together.
Okay, they're always together. Yeah.
Yeah. Yeah.
When you do isopropyl
Claire?
analysis, why don't we just stick on this line? Like, you sometimes go...
No, because the
that just-
liquid is changing, because if I'm precipitating A out of the liquid, the composition is becoming deficient in A, so it moves.
Oh, that's cold.
So I can determine my composition of my liquid just by following those.
Because as you're decreasing A,
It's only what?
because of this change of...
Well, no, A precipitates out, so that's the response.
That's the response. Whereas if it was here, because it's just straight lines, that's why.
Except for that.
Oh. The liquid follows the liquid. The composition always has to stay on the liquid. The liquid always.
Yeah. Are you?
I've got...
All right. Let's get going here, huh? Okay. I brought a book. I don't know if I'll use it today, but this is one of the volumes of phase diagrams of ceramides. A number of years ago, I asked the library to buy the whole set in hard copy, and for some perverse reason, they put it out on the stacks where you can borrow it. Normally, it's in the reference section. So we've got a full set of the hard copy in the library. These are compendia of ceramic phase diagrams. The metallurgists have their own compendia. They're huge. And there are binary and ternary phase diagram compendia in the library as well, in hard copies. And if you get on the Landau-Bernstein tables, they'll all be there too. So there are many compendia. I also have a book on polymer phase diagrams, which is really weird, because nobody really thinks that polymers should be conducive to phase equilibrium, but some strange person decided to do it. So, right now, I've taught you everything you need to know for this class. Not much, is it? If I can do it in 3 lectures, that is not much to know. However, this class isn't about remembering and regurgitating what I've told you. Everything I've told you here is only of the most limited value. What's useful is using these diagrams to interpret them. You can interpret the results of your experiments, you can interpret the failure of some process or material, and you can predict how you might want to process. In Moodle, I've given you a definition sheet. These definitions you do need to know, not because I'm going to ask you to repeat them, but you need to know them because they're processes that I'm going to be referring to all the time. Like Czochralski crystal growth. Czochralski crystal growth. Okay. I told you when I did my master's I was growing crystals. I did not use the Czochralski growth method. That was really an easy method. I did something much, much more difficult. That was called floating zone. Liquid that was held within 2 solid pieces, and I had to keep that liquid zone coherent without running out because I was at such high temperatures I couldn't contain it. There's nothing would contain it. It was impossible. I had to self-contain. And Czochralski is a very well-known technique where you have a crucible and you have a melt of the material you have a rod, and you have a seed crystal. And you bring the seed crystal so it almost touches the liquid. You don't touch the liquid, the seed crystal dissolves in liquid. And then there's gas attraction. And then you pull the liquid up onto the single crystal. So the orientation of the single crystal determines the orientation of what you're growing. So the rod is turning, and it's slowly moving up. Quite slowly. And I've seen some pretty big boules, B-O-U-L-E, that were used to make the windows in spacecraft with single crystal sapphire. They were about this diameter. Somebody had a big melt of alumina, and a big crystal to start with, lowered it in and then pulled it up, and that's how they grow these windows and they slice them. This is called Czochralski crystal growth. And to have Czochralski crystal growth, you have to have a molten liquid of the same composition as your single crystal. So what does that tell you is a requirement for Czochralski crystal growth. What do we have to have? Anybody know? Sorry? That's correct. Congruent melting. If I can't melt it, how can I get a homogeneous melt? It's not possible. This is a prerequisite. If you're going to Czochralski crystal grow a crystal, you need a congruently melting phase. Now, did I mention about the early days of superconductors? We were growing crystals and physics and all that? Did I tell you that? Yeah. Okay, well, this was the principle. The physicists didn't understand this. And the superconductor was incongruently melting. Had it been congruently melting, everything would have been easy. They could have grown single crystals by Czochralski method, piece of cake. But they couldn't do that. So for Czochralski, I need congruent melting. For incongruently melting, we have what's called flux growth. Okay, so what I need here is to be able to precipitate single crystals out of the liquid. And then if I'm lucky, I can dissolve the solidified liquid away, leaving me with the single crystals. If I'm unlucky, I can pull them out, and I'll break them, but at least I can get the fragments out. If they're big enough, good enough to work with. Physicists don't need that much single crystals. Okay, so I want to grow some single crystals of A2B. And if I know phase equilibria, I'll know Tchaikovsky is not going to work. Because if I take pure A2B and I heat it up, I'm going to get A plus liquid. So my crystals are going to be wrong to begin with. So if I get a homogeneous liquid, okay. And as soon as I start to try to grow a crystal from it, all I'm going to have is the possibility of growing A. I'm going to have A2B, and it's not going to work. So it's just going to be a mess. It's not going to work. What's in this phase field right here? So do I have a region here where I can grow A2B out of the liquid and precipitate those secondary phases? Can I do that? Will that work? Suppose I take the composition, I go off composition, and I told you that the other day. I go off composition, and I heat it into that zone. Yeah. And what's going to form? A2B in liquid. So, if I'm clever, what I could do is, if the A2B crystals float, I can skim them off. I don't have to cool it down. But if they sink, I can pour the liquid off. And then get rid of most of the liquid, and then I got the crystals concentrated at the bottom. Or I can just let the thing go in a crucible and pick them out later on, whatever. So there's three ways I can approach it, but I'm stuck with the problem of a matrix with crystals in the matrix. But that's the only way I can do this. And as long as I have crystal plus liquid, I can do flux growth. And that's your alternative. And by the same token, I may want to densify. So I can have solid state densification, which we also call sintering, or I can have liquid phase sintering, densification. Now, you need to erase from your mind this idea that materials are always cast into shapes. That's not the case at all. Many metals can be cast into shapes. Rolled and swaged and drawn and what have you. But metals we can melt usually and pour into a mold. We can't do that with ceramics. One ceramic reaction melts, refractory. We don't melt ceramics because they crack. There's a huge volume change from the solid. It's brittle. So we sinter, we densify. And a lot of metals are densified this way too. We don't melt all metals, we can sinter them as well. And we do this in the solid state, which means only solid, or we can speed up the process and get a little bit of liquid. And that liquid is a diffusion path, and densification requires diffusion. So we speed the process up, and the liquid also allows particle rearrangement, and the liquid has capillary force, suction, surface attraction, so it pulls the particles together. So getting a little bit of liquid is a big advantage if you can control it. And this is what we call liquid phase densification. We might have up to 20% liquid. We might need only a couple percent. Depends on the system. Sometimes these liquids are glass, and then they're there afterwards generate a little bit of liquid, we can have liquid phase densification. So for solid state densification, there's only one requirement. It'll form a liquid. So if I want you to solid state densify A2B, okay, I want you to solid state densify A2B. What is the maximal temperature that you can do this at? T1? Who said T1? Why did you say T1? Maximal temperature centering A2B. I'm pure A2B, okay? Pure A2B. I'm not all composition. I think that's where you're thinking. All right, it's pure A2B. I'm centering none of this. What's the temperature max that I can use to center A2B? T2. Because above T2, I've got a paratectic decomposition. That's really bad. I don't even have any more of that. Anywhere up to that, I'm safe. And typically, if you have no idea what to center at, you'll see the temperature between 75 and 80% or 90% of the melting point of that phase. Of course, this phase doesn't have a melting point. So you would choose it, that proportion, to the paratectic decomposition temperature. Okay? All right, so that's solid state sintering. But it's slow, and it's often leads you to pores, and it's not often all that brilliant. In fact, up until the early 1960s, it was universally believed, and the theory was already laid out, that it was not possible to achieve full density in ceramics. Universal theory, you could not densify a ceramic fully. And then Don Ullman and Bob Kingery discovered how to do it. They pinned the grain boundaries with tiny little precipitates. When they pinned the grain boundaries, the grains did not move and absorb the pores that were stuck between. As grains grow, they can grow over the pores, and you're always stuck with intragranular porosity. They figured out how to stop that, and they got fully dense aluminum. Revolutionized ceramics. About 1961, that was done. Bob Coble was the third guy at MIT who did that. Okay, so everybody thought in those days you could do it, so liquid phase densification is where you got to go. And today we still use liquids all the time because it's an advantage if you can manage it. So A2B has the possibility of liquid phase densification, doesn't it? Can I do liquid? Is there something on the phase diagram that tells me I can do liquid phase densification of A2B? Raise your hand if you don't know the answer. Okay. To do liquid phase densification, I have to have a liquid that's compatible with the solid. Do I have a phase region that has a liquid compatible with the solid? Yes? Same as the flux growth. Liquid compatible with solids. So this region right here says this is my working range for liquid phase densification. So the exam question is, what's the minimal temperature for liquid phase densification? What's the maximal temperature for liquid phase densification? Okay. And then you would say, well, if you want 10% liquid at the midpoint between T1 and T2, I want 10% liquid. Well, here's my lever, and 10% liquid, I just measure it up. Give me the composition that you need to batch to do liquid phase densification at that temperature, generating that level of liquid. That's called engineering, material engineering. Okay, so flux growth is the same as liquid phase densification, same requirement. If you have solid compatible with the liquid, you can do both. Okay. Easy. Okay, so these four terms, liquid phase and solid state densification, and Czochralski growth and flux growth. These are principles you need to understand because these are processing. And you can use this knowledge to make a better material, which is what my professional goal has always been. I want to make a better ceramic. One of the most famous phase diagrams in ceramics is the alumina silica phase diagram because so many systems have these two oxides in them. Now I know this phase diagram by memory because I refer to it all the time. Every ceramic engineer probably has a working knowledge of this diagram. There's one intermediate phase. It's 3 alumina, 2 silica. Okay, so AS are short forms for alumina and silica. This is called mullite. It shows a limited solubility region here, a few percent. Okay? There are actually two variants of this phase diagram where mullite is either congruently or incongruently melting. Depends a bit on the raw materials, the way you heat it, the kinetics, and so on. But generally, we tend to treat it as congruently melting. Aluminum melts at about 2020. Silica melts at 1673. Mullite melts at 1850. Sorry. I usually remember this. Better check it out just to make sure. Yep. Must be getting Alzheimer's. 1595. Okay. What does this diagram tell us? Well, this is the basis for many refractories. The entire phase diagram is used to make different refractories. We can have high silica, we can have high alumina. First thing we can see is that the general slope of the liquidus is like that. So we can see that silica is a flux for alumina. The second thing we can see is that mullite is a pretty refractory phase. It is the only reaction product in this system. So if I put those two together, I'm always going to get mullite in equilibrium. When we make a brick, we make clay. Clay is largely alumina and silica. But we don't usually get mullite because we don't fire a brick to a high enough temperature so that it forms. So bricks are not at equilibrium. A lot of glass in bricks, that's what gives them strength. But I just did a study on a heritage house from the 1820s, Francis Greenway house, and I analyzed the bricks in that house. I'd also analyzed the bricks in the first government house from 1788. And I was very, very surprised to see that both of those bricks contain mullite. That was a huge surprise to me. I did the government house a number of years ago, but I did this other one just recently. And the reason why that mullite was there was because I've got a book that talks about early brick making in New South Wales, and the author says that most of those bricks were fired at 900 degrees for 3 to 4 days. And typically you need 1,000 degrees to make mullite form. But when you heat it for a very long time, can't get the temperature, you extend the time and give enough time for diffusion to take place, which would be faster at a higher temperature, but it's slower at a lower temperature because you still get the same extent. But today, if we analyze bricks, we're almost never going to find mollite in them because they're all fired quickly and they want to reduce energy costs. But in those days, well, throw them in a pit and fire them for 3 days, okay. So mollite is not an easy phase to form, but if you do get it, it's quite stable. And mollite's a really attractive phase. It's stable in oxidizing and reducing atmospheres, has a low coefficient of thermal expansion, so it doesn't have thermal shock problems, it's very corrosion resistant, it's high strength, it's low density. It's a really attractive product. So the first thing we look at is the slope of the liquidus surface. The second thing we notice is the temperature drop from here and to here, and the steepness of the liquidus surface. So we look at alumina side, and you see the temperature drops from 2020 to 1840. Well, it's 160, 80 degrees, 180 degrees. But it takes you well into the diagram. On the silica side, it drops 78 degrees, but that's actually at about 5. It drops really quickly. So the conclusion from this is actually that alumina is a very powerful flux for silica because of the steepness of that liquidus surface. So a little bit of alumina has a big effect on silica, but a little bit of the silica on alumina doesn't have that big effect. Even though if you stretch it all out, you'd say, yeah, it's bigger. But on a percentage-wise basis, just look at the slopes of the liquidus surfaces. And you can see that actually alumina is a more powerful flux than silica at low levels. Okay? We can see that if we are on the silica-rich side of the phase diagram, the initial temperature of liquid formation is what? What's the initial temperature of initial liquid formation? 1595. Come on, I wrote it for you. If I'm on the alumina-rich side of the phase diagram, what's the temperature of onset of liquid formation? 1840. That's a big difference. So if I'm making refractories, I've got 245 degrees difference. That's huge in refractory world. Alumina is more expensive than silica. You go use different raw materials and much more expensive processing, but you can have a better performance. Alumina has a high coefficient of thermal expansion, though, so you have thermal shock issues. Silica's also got some issues because I haven't drawn something on here. We'll come to that in a minute. It's got its own issues. But I'm just looking at this diagram here. Can I liquid phase densify mollite? Can I liquid phase densify mollite? You should be able to look at that and say, yes. If you can't do that, you're behind. What's in that big triangle on the silica-rich side? What phases are present? Is that a big region? What's in this one? Right here. They're both mollite plus liquid. There's an important message here. If your composition is slightly alumina-rich, you're going to have problems doing liquid phase densification. For 2 reasons. First is the required temperature is much higher. And the second is the flexibility that you have in terms of composition and temperature is very small. And these are naturally occurring raw materials, so they vary. And you could very easily find yourself outside of that two-phase region, and then you get complete liquefaction, or you don't get the right phase. You don't get liquid phase densification. But on the silica-rich side, you can see that we can liquid phase sinter this starting at 1595. And the less liquid I have, the better. So now I have to define refractoriness. A refractory is a high temperature resistant material, and it depends on two things. It depends on the temperature of liquid formation, but it also depends on the amount of liquid. Okay, it's those two things. Usually, if we're just doing a quick assessment, we just look at when the liquid forms. We have to do both to get it right. So that tells you, if you want to liquid phase densify mullite, you better choose some compositions around here. You want to minimize the liquid for two reasons. You need to get the right amount so you don't lose your shape. If you have too much liquid, you'll sunk your shape. And then when you perform at high temperatures, the more stable it's going to be because it's got less liquid. So that's kind of the name of the game here, minimizing the liquid. So this diagram is a good one to tell you the importance of choosing the right two-phase field, because if you're too narrow or too short, your temperature fluctuations in the furnace or your raw materials variations are going to kill you, and you're going to have big disasters. So choose a phase field that's big to work in so you can have flexibility. So alumina-rich, much more refractory than silica-rich. Silica-rich is also better for liquid phase densification. I could Czochralski crystal grow mullite, as well as alumina and silica. And I can see that low levels of contaminants, and when I'm talking about low levels of contaminants, alumina is a much more powerful flux than silica, because of the slope, so the liquid is surface. But for the whole diagram, silica is a flux for alumina. And so when we grade the quality refractories, we will see a direct correlation between the amount of alumina and the performance, thermal performance. Okay. Does A dissolve in B or B dissolve in A? Who thinks A dissolves in B? Well, what is it? You raised your hand. You down. Nobody else raises a hand. You can't do that on an exam. Who thinks B dissolves in A? Oh, come on. You already put your hand in. Come in and yourself. Of course, B dissolves in A because A has the composition that comes out. That's the matrix. I want to densify B. What's the maximal temperature I can do solid state densification? Maximal temperature of solid state densification of B. What is it? The melting point. Okay. That's a no-brainer. Okay. What's the minimal temperature for solid state densification of B? Pure B. Yeah, I know you think. Pure B. Minimal temperature for solid state densification We don't know. There's no way to tell. There's no justification for giving an answer. I just told you it's 75 to 90% of the melting point. It's just a ballpark. Okay? So the correct answer is we don't know. What's the maximal temperature for solid state densification of A? What is it? Melting point of A. Okay. Solid solution. There's a big solid solution there of A, we could call it alpha, or A sub SS, AS. When we make a solid solution, we're putting ions of B into the lattice of A, aren't we? Are those defects? Are they structural defects? Yes or no? Who does not know the answer to that? All right. The lattice of A, a single crystal of A, consists of A only. It could be an oxide, it could be an element, who knows? We visualize it as a perfect lattice. Might be polycrystalline with grain boundaries. Those grain boundaries are defects because they disrupt the lattice. If I dissolve B, I put in an interloper, a contaminant, a foreign ion. It is a defect. It might be an interstitial defect, it might be a substitutional defect, but it is nonetheless a defect. And defects help densification because they act as nucleation sites, and they also act to enhance the hopping mechanism for diffusion. So defects are good for densification. So this knowledge allows us to speculate that it might be relatively easy to densify A more easily if we dissolve some B in it. Because you can see that the refractoriness, the temperature at which liquid forms, is going down the more B we put in it, isn't it? So B is flux for A. So if I take some B, throw it in there, it's going to lower the stability, the refractoriness, create defects, and enhance densification. Well, that's a good thing, provided that I don't change some other properties that are priority to me. Defects are bad for mechanical properties. On the other hand, if you're increasing the density, that will improve the mechanical properties. Defects are bad for thermal properties. As you can see, B is a flux. So I may degrade the thermal properties, but I may be okay and actually improve the mechanical properties. Maybe I want to make this translucent. It's got to be very dense to be translucent. Improve the optical properties at the expense of changing the chemistry. It really depends on what your other considerations are, but this is a good way to achieve better density if you know how to interpret the diagram and you know a little bit about material science on top of that. I've drawn an inverse paratectic here, and your job is to investigate the possibilities for system AB for whatever applications you have. So you're given this wide scope of project, figure out, what happens when we mix A and B together. So you're going to heat them up to equilibrate them. And rule number 1, always start with your end members. I have a postdoctoral fellow who's worked with me for 10 years. We've been continuously funded by a company that has fly ash deposits. And they asked me to come in because they were unhappy with their original partner. And so I did, and I said, show me what you've done. And I was stirred at what a crappy job had been done because they did exactly what everybody else had done. They were trying to make molite with fly ash, with glass and molite crystals precipitated in glass. And if you want molite, the glass has got high silica, so they were adding alumina to drive the composition onto molite because they wanted to make refractories from this. Very counterintuitive because glass is very bad as a refractory. And I said, you should have investigated the end members to start with. You've gone right on to the composition of molite, and you've done exactly what everyone else does. You're not going to get any patents that way. So the very first experiment we did is what led to our patents, starting with pure fly ash. And it was a shock what happened when we did what nobody else did, which was long-term heating, just simple stuff like sample shrinkage and long-term heating. Nobody had done that. And nobody looked at pure fly ash, that end member. And that's what led to 4 patents, just starting with end member. So if you're given a job to investigate a system, you need to know the starting point, which is your end member. So you're going to take this composition A, and you'll probably do a series of compositions across here to get the lay of the land, to see how this stuff performs. And you're going to heat them all up, same temperature and time conditions, so you get a level playing field and see what happens. So this is the temperature you're going to choose to kick things off. So there's an isotherm across there. And we're going to have this composition and this composition, this, and this. And we can read it right off the phase diagram what's going to happen. Actually, from this you can construct the phase diagram. You need to do a bit more, but it's the starting point. And if we take these as compositions 1, 2, 3, 4, 5, 6, 7, 8, composition 1 is just solid state A. Okay, that's not going to be very exciting. Maybe it'll densify, maybe it won't, who knows. Composition 2 is going to have a lot of liquid in it, isn't it? So it's lost its shape. We press the pellet and it spread out. Not too good. Composition 3, on the other hand, we had a big chemical reaction, and the pellet fell apart into a powder, but it didn't melt. Composition 4 had a fair bit of liquid and it slumped out again. Composition 5 completely ran off or sank into the brick that we were using. Totally liquefied. Nothing left of that. Composition 6, rounded. Composition 7, only slightly deformed. Not as much liquid. Composition 8, nothing much there. Okay? So you figured things out, and the most interesting one you got here is the intermediate phase. You go, that phase is not liquefied at the temperature I chose. I'm going to raise the temperature up and find out. Or better yet, I'm going to synthesize it as a single phase, and I'm going to put it on a DTA-DSC and see what happens. And that will reveal when it forms a liquid. And I will have this point. And once I've melted that dude, I'm going to put it in an optical microscope or electron microscope, and I'm going to look at it. And all I'm going to see is a single phase. I'm going, congruently melting. Excellent. Only a single phase. And it's at 30%, so we'll say it's a 33, and that will make it a 2B. Whoops, wrong place. Okay, so I can use the electron microscope to get a composition. I can do chemical analyses, whatever. And I'll figure out its H2B, and I'll have its melting point from the DTA to C. Or is that really what I'm going to find? Does that actually happen? That'll happen if I'm not at equilibrium. And I cooled it down rapidly and everything hung around. But if I'm at equilibrium, I'm going to be completely mystified because every single sample is going to be A plus B because this is room temperature. At room temperature, everything's disappeared. I might have a eutectic microstructure between A and B, and that's to be expected. I'm going to have A and B. And depending on where I am, my primary phase will be A or B, and I might have a bit of A to B in there too, and I'll know at least I got three things in there, so I'm getting some knowledge. But at equilibrium, all I'm ever going to see is A and B. That's not very helpful. So you need to remember that. Everything is going away. A to B is undergoing an inverse paratectic reaction. That's not too good. So that complicates things. So if you have a system like this, it's going to be a bit difficult to study. There are some other things that can happen. We can have this, we can have this, and we can have this. Now these are all oids. So I'll put some solid solutions up here. Okay? So the one on the left is an upward decomposition, which is paratectoid. The other one is a downward decomposition, which is a eutectoid. And the other one has both upper and lower, and we don't have a name for that. So it exists only over a narrow temperature range. The only way we're going to find that is if we have traces of it that have been retained metastably, or we do high temperature X-ray. And we can heat the X-ray unit up into that range, we'll get that phase showing up. So these are some other complications that make it a little difficult sometimes to do phase diagram determination and to know what the heck's going on, because things aren't supposed to be there at equilibrium, and the only reason we see them is because we're not at equilibrium. That gives us a hint. This is why many times we quench things. Okay. And quench means rapid cooling. And the idea of rapid cooling or quenching is to freeze in the high temperature microstructure, to not give enough time for diffusion to reach equilibrium. And it's very, very commonly done. I did it for my PhD thesis, which was a phase diagram for the quaternary one. Quenched everything really fast, over about 30 seconds. Just Michael Ferry does about 1 million degrees a second. It is really fast. But he's trying to prevent metals from recrystallizing. They diffuse very quickly, so they've got to cool really quickly. The ceramics, they're much slower. 30 seconds was good enough for me. So I quenched everything, and that's what you try to do, to freeze in the high temperature phases, and that's usually considered good. Usually gives you a picture of what's happening, an accurate one. Okay. But we have these complications, and these are a couple of examples I haven't shown you.